cutie patootie. Welcome back to Decaf-Math ASMR, and a very warm welcome if you are new here. It's wonderful to see you. I hope that you're doing well. Today, let's have some relaxing fun. We are going to be playing around with the idea of adding fractions with different bottoms, different denominators, or you might call them uneven fractions. And we're just going to take our time and just build some intuition behind it today. I assume that if you're actually watching this to learn, that either you like this slower intuition-based learning, or maybe you've learned the how-tos, maybe watched a quicker tutorial and it's just not quite clicking. So either way, we're gonna let this information kind of simmer, and then we can come back and do some extra practice problems down the line, okay? Good. As always though, it doesn't matter whether or not you're learning this, if you know it, if you don't, if you think you're awesome at math, if you think you're terrible at math, somewhere in between, it doesn't matter at all. We're just here to enjoy the moment, and I'm just happy that you are here. Okay, so why don't we first look at this example. What are these two fractions? We have 1 over 2, 1/2, plus 1 over 4, 1/4, right? Good. So we are going to be adding these two fractions, okay? And to add fractions, let's draw out what these fractions look like. So this is a little bit of review before we just jump into the rules, or before we just try and solve it all at once. Let's build some intuition, okay? So what does 1/2 mean? What does this mean? Okay, so if I said this circle represents 1, it's one whole thing, how would you draw or shade in maybe half of the circle? What would you want to do? Is, for instance, this, is that half of the circle? Not quite half, right? Half would mean that our two parts are the same, exactly. So we'd want to shade in a little bit more. So we're going to break this up into two equal parts. You can do this lots of ways on a circle, especially just all these lines through the center. But I'm going to go ahead and just do this. Just keep it simple, okay? So these two halves are the same, right? So close enough anyway. They should be the same. And so the bottom number tells me how many equal pieces should I cut my hole into. So in this case, 2. 1, 2. The top number tells me how many of those pieces do I have. Like, am I going to shade in? So one of these two is what I'm going to shade to represent 1/2. Okay, good job, dear math angel. So this pink piece represents 1/2 of our whole, right? Good. This is also 1/2, but we are focusing on the piece that we are shading. Good. So 1/4 is the exact same thing. We can have let's say this circle represents a whole. The bottom number, the 4, tells me how many equally sized pieces we cut this into. So in this case, 4. You can do this again however you want to, as long as all 4 pieces are the same size. I'm going to go ahead and cut it like so. 1, 2, 3, 4. And the top number tells me how many of those pieces am I going to shade in. In this case, 1. So I might as well pick this one. Okay, very good. So the blue part represents 1/4 of the whole circle. Good. So now, how do we add these pieces together? Now, before we do that, let me note that we are talking about a proportion here. This piece relative to this whole thing is 1/4, but we don't care about the actual physical size of this thing, because if I had a huge circle like that and I break it down into 4 equal pieces like that, and I color in one of them, this is 1/4 of the whole circle. But this piece is really big compared to this 1/4. This 1/4 of this huge circle is almost physically the same size as the area of the half of this one circle. So we don't talk about it like we don't compare it with the physical actual size, okay? We're just trying to talk about it as a proportion. So with respect to this circle, this piece is 1/4 of it. With respect to this circle, this piece is 1/2. So we're not just going to pick this piece up and put it right there as an area. But these two circles are kind of close in size. So if we were to do 1/2 plus 1/4 in one picture, it makes sense to standardize the whole thing that we're talking about, the circle. So let's just go ahead and smush this picture into this one by redrawing this idea of 1/4 on the same circle, rather than thinking of picking this 4th up and putting it here, because the circles are not the same sizes. Does that make sense? So we're going to do this 1/4 again, but on this same circle, so that we are standardizing the 1 and therefore doing everything relative to the same thing. Okay? Does that sound good? Okay, good. Okay, good. So now we have the circle again. We have our 1/2, which is our 2 equal pieces, and we shade in one of them. Now, for 1/4, we need to break this up again into 4 equal pieces, and I might as well break it up like this. And I say might as well because I kind of have a point with this picture, and that's how I set it up. But in general, you can do this theoretically however you want to. You can cut this up however you like and add 1/4 on top of it. It's just that if you have overlap with the pink part, you'll have to remember that there's an overlap. So when you try and sort of represent the sum, the total, you want to remember to kind of move that piece off of it to represent the total area. So in this case, if I do the 4 pieces, 1, 2, 3, 4, I can color in one of those 4 pieces for 1/4. So I'm going to color in this one. You see that? So I have no overlap between the pink and the blue. Now, when I want to know what the total is, I'm looking at the total shaded region in this entire circle. So I might observe here that I have 1, 2, 3 pieces, and each of those pieces are 1/4 slices. It kind of looks like, first of all, that this pink area is now 2 of those 1/4 pieces. So that's an interesting thought. Maybe somehow 1/2 and 2/4 are equivalent. And then we added 1 more fourth to that here. So now we have 1, 2, 3 of our 4th size pieces. So our hypothesis from this picture seems to be like, hey, maybe our answer is 3/4. And indeed it is. But let's use this picture to give us a little bit of an idea of the two rules, right? So it seems like if somehow this half is the equivalent to 2/4, then 2/4 plus 1 more fourth is equal to 3/4. And that indeed is a rule. If we have the same bottom number, we can just keep that bottom number and add the tops. So if you want to write that out, two-fourths plus 1/4 is 3/4. If you're a visual learner, you can add in some colors and emphasize that you keep the 4s and you go ahead and add the tops. So I can make a note that you add the numerators. And intuitively, based on our breakdown with fractions, that makes sense because the bottom numbers again tell us how many pieces to break the circle down into. So we're not doing 4 plus 4 is 8 because the pieces tell me sort of the relative size, right? If I break it down into more little pieces, then a little 1/10 piece would be smaller than a 4th piece, right? So we don't want to do a 4th piece and another 4th piece gives me an 8th piece. That's not quite true. We just say, oh, we're adding a 4th piece and a 4th piece together and another 4th piece. Oh, that's 3 4th pieces. Very good. So our first rule for our game is that if the denominators are the same, then you keep that denominator, that bottom number, and you add the tops and you make a new fraction, okay? So that's rule number 1. And then rule number 2 for adding uneven fractions is how did we get that 1/2 and 2/4 are equivalent? So we want this idea of equivalent fractions. So the rule for equivalent fractions is if I multiply the same number on the top and the bottom of a fraction, I get another fraction that is equivalent to my original one. So if I have 1/2, to get to 2/4, I multiplied by 2 on the top and on the bottom. That gives me 2/4. 1 times 2 is 2. 2 times 2 is 4. So 1/2 and 2/4 are equivalent. I can multiply any number I want besides 0 to get an equivalent fraction. So I could multiply by 5. 1 times 5 is 5 over 2 times 5 is 10. 5/10 is also equivalent to 1/2. So that's my rule number 2. If you've learned about simplifying fractions, then you might recognize that you can work the other way around. To simplify 5/10, I can see that 5 goes in the top, 5 goes in the bottom. So if I divide that out, I get 1/2. So this is kind of the opposite direction. It's the other way around. And if you want to kind of have some intuition about why, we've actually kind of talked about that here on this channel. But I think it's quite fun. So let's do that. 1/2 times the 2 on the top and the bottom again. What this really is about is the fact that for fraction multiplication, you can multiply across the top and on the bottom. So without getting into it too much, basically I can split this out here because 1/2 times 2 over 2 means I can multiply across the top 1 times 2 over 2 times 2, which is this. So I'm kind of pulling that 2 over 2 out to the side. I cannot do that for addition. By the way, it's not 1 plus 1 over 2 plus 4 like we talked about earlier, but for multiplication, it is. So if I pull the 2 over 2 on the side here, 2 over 2 is 1. It's another way to write 1. You can think of it as 2 dividing by 2, which is 1. Or you can think of it as, based on our drawing from before, we would have the bottom number tells us we split our circle into 2 equal parts. The top tells me I have all 2 parts, so that's the whole circle. Same thing for 5 out of 5, 10 out of 10. So as long as the top number and the bottom number are the same, I get something that's 1. It's like another form of 1. So it's 1 in disguise, and 1/2 times 1, or anything times 1 for that matter, is itself. 1 is this very special number for multiplication called the multiplicative identity, meaning 1 times anything is itself, and anything times 1 is itself. You just have one of them, just like you. You're unique. One of you is you. That's a silly example, but 1/2 times 1 is 1/2. So as long as you're multiplying different forms of 1, you're getting something equivalent. So in this case, as long as our top and bottom numbers are the same number, usually we kind of skip over this logic, but this is kind of the background information. But if you multiply the top and the bottom by the same number, you get an equivalent fraction. So in this case, we multiplied by 2 on the top and the bottom so that we got a 4 on the bottom. And then that way, using our first rule, we can keep the 4 on the bottom and add the top numbers. So now let's put that together. What was our first goal? Our first goal is going to be to make sure that they have the same bottom number. How do we determine what number that should be? Well, there's not one right answer to that. In this particular case, we noticed that 2 times 2 is 4, so we don't have to do anything with this 4, but I can multiply by 2. So the order that we would think about this is I'm going to multiply 2 by 2 to get it to be 4. But I can't just randomly multiply by 2 because I feel like it. What happens here? Well, because I multiplied by the bottom, I need to also multiply by the top. So then we would get 2 over 4 plus 1 over 4 equals, and it's 4 all the way across, and then our 2 plus 1 gives us 3. So we get 3/4. Now, very, very good. Now, if we had different denominators and we didn't know what number it ought to be. Let's say we were staring at this and we didn't notice that 2 times 2 is 4, because that seems like, oh, you either get it or you don't. What's our overall plan here? Our overall plan is to somehow get them to have the same bottom number. It's all about multiplying though, right? Remember, we're multiplying the top and the bottom numbers. So we're not adding, we're not doing anything else other than multiplying. When we talk about factors and multiples, we're all talking about multiplying and dividing. So what I wanted to show you is that technically, if we did not notice 4 is what we call the least common denominator or the least common multiple of the 2 numbers in the denominators, which are the bottom numbers. And that just means what's the smallest number that both of these go into. They divide, right? So 2 goes into 4 2 times, 4 goes into 4 1 time with no remainder. Okay, so 4 is the smallest one, so we call that the least common denominator, least common multiple of the denominators. Use whatever wording you want, but theoretically you don't have to use the smallest one. Let's say you didn't note that, but you might notice, oh, wait a minute, I know that 2 goes into 20 and 4 goes into 20. Okay, just a random number that both of these go into. Well, you can do the same thing. If I wanted them to be out of 20, I just need to make an equivalent fraction with the bottom of 20 here and 20 here. So how do I do that? Well, to make this 20, I do 2 times 10, right, to get to 20. If I did it on the bottom, though, I have to do it on the top. Okay, so I'd have 10 over 20, which is equivalent to 1/2. To get 4 to 20, I multiply by 5. Very good. So then I would have 5/20. So if I add it like that, we do the 20 and 20. Now they have the same bottoms, and these are each equivalent to 1/2 and 1/4. I go ahead and keep the 20 and do 10 plus 5 is 15. If you're just tuning in now, if you're skipping through the video and you're tuning in now, this might be a little bit weird to see that I'm doing it out of 20, but my point is that we can do this with any common denominator to get our answer, okay? But if you notice here, we can simplify this. That's the opposite of our multiplying on the top and the bottom. I might see that I have a factor of 5 in the top and the bottom, as in 15 divided by 5 is 3, and 20 divided by 5 is 4. So we still get our 3/4 at the very end, okay? So our simplified answer will be the one that we get had we used the actual least common denominator, the least common multiple in the first place. So in general though, if you're staring at it and you have no idea what to do, what number do these both go into, I would say actually the safest thing to do is you can just multiply them together, because 8 will be a multiple of 2 and 4, because if I do 2 times 4, I literally get 8. So 2 times 4 here on the top and the bottom, 4 times 2 here on the top and the bottom. At the very least, we're going to have a multiple of both by multiplying these numbers. But if you happen to notice something else, or you can use our prime factorization tricks that we've talked about on this channel for fun, you can start by trying to find the least common multiple, and if you can't, you could just resort to multiplying them, or you could just guess a random number, see if you can find something that they both go into, okay? just make sure that when you get a final answer that you go through the process of listing out some factors. So you kind of go through 1, 2, 3, 4, not one, but maybe 2, 3, 4, 5, that kind of thing. Go through the factors and see if there's a common one. And if there are, then you cancel them out until you get something where the only common factor is 1. So 3 and 4 don't simplify any further. Good. Very, very good. They don't they don't have any other common factors besides 1. So that's it for now. Let's work through one more example before I let you go. And we're going to just let that simmer. Okay, so we're going to put these pieces together. And like we said, we can work through an entire worksheet together sometime as well, so don't worry. Just hope that this gets you started. Okay, so now let's say we have 2 sevenths plus 4 ninths. Okay, so now you see the top numbers are not 1. It's okay. We follow our same exact rules. So this one, if we were to try and sketch the sevenths and the ninths on one circle, it's going to be a little bit trickier because trying to break down a circle into 7 equal pieces is kind of rough. 9, at least I can kind of break down the 360 degrees. If you've done some geometry, I can break that evenly and kind of try and measure it. But either way, it's kind of hard to, cut a pizza up into 7 and 9 equal pieces, right? I'd like to be the one with the bigger piece. Not really. But it's hard to sketch that out exactly, but that's the same idea. If you were to break up a whole into 7 equal pieces, this would be 2 of them, so I'd shade in 2. If I broke it up into 9, I'd shade in the 4, and then that's how I would represent these 2 fractions. But now that we already sketched it out for the other fractions, we can use the same rules, the same idea, right? We want to make these each have a common bottom number and use our equivalent fraction trick by multiplying the same number on the top and the bottom to add. So we're only looking at these bottom numbers now. What is a common number that 7 and 9 divide into? What's our common multiple here? Our least common multiple ideally, but any common multiple would be fine. So you might kind of stare at this, you might kind of guess, maybe about 49. 7 goes into 49 7 times with no remainder. 9 doesn't go into 49. 9 goes into 45, but not 49. So not quite. And then you might kind of stare at it for a while. You might, if you want, you can even list out some multiples. So 7, 14, 21, 28, 9, 18, 27, 36. I'm not seeing anything in common though. And in order to do these, I'm basically doing 9 times 1, 9 times 2, 9 times 3, 9 times 4, right? 7 times 1, 7 times 2, 7 times 3, 7 times 4, Nothing in common so far. If you do want to use our prime factorization trick, you'll notice that 7 itself is a prime number. This is 3 squared, so it's actually going to be 7 times 9, which is 63. But even if we can't confirm that, we can just go ahead and do that thing where I was saying that if you're staring at it and you can't come up with one, then you might as well try to multiply them. It's not going to hurt as long as you remember to always go back and simplify your final answer. So let's stick with 63. 7 times 9 is 63. So we want to make this into a fraction with 63 on the bottom, an equivalent fraction, and this with 63. So that our answer also has a bottom of 63. Now we can actually add them. How do we do that? Well, to get from 7 to 63, I multiplied by 9. If I do it on the bottom, I have to do that here. 2 times 9 is 18. So 18 over 63 is equivalent to 2 over 7. How do I do it for here? 9 times 7 is going to give me my 63. It's all about multiplication. 9 times 7. If I do it on the bottom, I have to do the same thing up here. 4 times 7 is 28. Very good. And now I can add 18 plus 28. You can do that on your calculator, I suppose, but we can just scribble it out. Actually, ideally, we scribble it out somewhere on the side. Okay, so we don't get confused, but I don't think you can see this now. But a plus 8 is 16. 1 plus 1 plus 2 is 4. Either way, we'll get 46. 46. And that will be our answer. In this case, we know that 63 is our least common multiple, least common denominator. So we don't need to simplify this any further. It won't be able to. However, if we were not sure, we would factor out 46, maybe list all the factors. So we would do like we try 1, 2, then maybe not 3, not 4, not 5, blah, 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 blah. I think it's just going to be 1, 2, 23, and 46. And list this out and make sure that there are no factors that are in common. So no numbers that go into this and this besides 1 without any remainder. And in this case, I'm pretty sure we are good to go for that. Okay, I hope that this is making things clear and that this helps. Let's do some extra practice later on. But again, takeaway, you want each of them to have the same bottom number so that we can keep it and add across. And in order to get them to have the same bottom number, we multiply by the top and the bottom by the same number. That gets us to the denominator that we want. To determine what denominator we should use, we can by default multiply them together. But in general, ideally, we find the least common number. Oftentimes, it's not just multiplying them, unless one of them is prime, and it's a very specific situation where that's the case. But otherwise, we'll want to find a number that they both go into evenly, and ideally the smallest one, so that we don't have to go back and simplify again. Okay? I hope that makes sense. I love you lots. Take your time with this if you're struggling with it. Otherwise, I'm really glad that you came here to relax with me. Thank you so much. Thank you for your kind comments. And I will see you around for more math very, very soon.